Hey everybody, so today we're going to actually be starting off looking at a new project, and hopefully we can turn this into a whole series on problem solving and looking at a couple different programming languages to solve this problem. So overall what we're going to be doing is making a state machine. If you don't know what that is, don't worry, we'll explain it throughout this video. But the whole goal of this project is we're kind of going to have a state machine. We're going to be transitioning around states and outputting what state we're currently on, and then when we're done, the user can just enter exit and they'll be done. So that's kind of the brief overview. So let's understand a little bit about what state machines are and kind of the more formal computer science parts of state machines and deterministic finite automata. So state machines, or more formally, deterministic finite automata, or DFAs, are useful for multiple facets of computer science and practical applications in real software. So how do we describe this? And I think once you see what the image is, we can start to better understand what's actually going on. So this is a kind of overview. This is a really simplified example to just kind of get the overview, really. We have states. In this case, we have waiting or listening, and we start somewhere. An action occurs and we transition from one state to another, and then another action occurs, we transition from one state to another, and we keep going through this. And it tells us, this one diagram tells us all the functionality and how it's going to work. So for this basic example, we start in this waiting state and we have a personal assistant that shall not be named, that when we say their name, they're then listening for the rest of it. And then when we ask them a question, they answer the question and they stop listening and they go back to that waiting state. And this gives us some helpful things about what we know about the functionality of it, which is I can't immediately go from the waiting state to saying something, to answering a question. And right, that makes sense. And so because our state machine says we have to go through this, it means we can know from a functional standpoint that when we implement this, there's no physical way to go from this state to this state without previously going this path. And so that's a really useful piece of knowledge. So if you think about something that's like a hardware application and you need it to go from one thing to another and it can't mess up ever, if we set it up this way and we coded it right, then it physically can't. There's nothing that allows it to go right from one to the other, at least the way we have it right now. So potentially you could be adding more states. And so this is a very simplified way of looking at it. And this definitely is not how the actual personal assistant's working, but this is an example of how you can conceptualize how it might be working. And so as I said, there's a bunch of things we could pull out from this. We know that it's going to loop forever. We know that to ask one question, we have to say the key phrase to then have it listen. And when it stops listening, we have to say the key phrase again to have it listen again. There's a lot of things we can tell about it by just breaking it down into this kind of functional, this state diagram. And so you can read through this if you are inclined. All of this will be posted as well, so you can check out the link in the description if you want to read more. So more formally, we can look at these as DFAs. And a DFA is defined from Wikipedia as having 5 particular things. It has a set of states. Well, that makes sense. If we're making a state machine, we'd hope it has states. We have a finite set of input symbols, and that might be a little complicated, but we'll look at that in a little bit. A transition function, which is really just defining how we go from one state to another. An initial state and an accept state. And so let's look at this basic example here. We have a bunch of states. So we could say our set of states is S0, S1, S2. That one's obvious. Okay, so that one was easy. A finite set of states, Q, is S0, S1, and S2. And what we're going to do is we need a set of inputs. And so the last example was kind of an arbitrary example. We just gave it, the commands we'd tell our personal assistant. In this case, we have a set number of inputs, and we have a particular set of inputs. In this case, we can input a 0 or a 1. So we'd start here, and we have if we get a 0, we go from S0 back to S0. If we get a 1, we go from S0 to S1. And then once we're in S1, if we get a 0, we can go to S2. If we get a 0, we go back to S1. And you kind of just follow it. we have inputs, 1 and 0, and we have states that we transition between. So we kind of just said it. What are our input symbols? We know in this case the set of input symbols is 0 and 1. Now we have a transition function, and this is kind of complicated to look at, but in reality, what is this saying? It's all of what we kind of know from the diagram, which is when we're in a current state and we get an input symbol, we go to some next state. And so we can write this information out as a table with all of the current states times all of their input symbols, because every current state is going to have an input symbol that we can handle from there, right? Because every state should be able to handle all of the inputs. At least that's how it's going to work in a deterministic finite automata. From here, we have our start state, which this one's kind of obvious. We have the arrow pointing to S0. So we know S0 is our starting state, which is, from the set of all states. That one's a little confusing, that wording there. It's from the set of all states. Basically, what that means is the starting state has to be a state. It's really that simple. And then from there, we have the except states, which we're not really going to be looking at much in this program, but in terms of theory of computation and stuff like that, you should know that if we end in an except state, that would be a valid thing. Whereas normally we'd be checking if we end in an accept state or a non-accept state. And those are going to be written out with the double circle on the symbol. So if you notice, S1 and S2 have the single circle, whereas S0 has the double circle. That means S0 is an accept state. And so from there, so this is kind of the formal stuff. So let's take a step back to remember what was our initial thing. So we have this deterministic finite automata, or a state machine. And what's our overview? We're going to read a file containing the states in transition. So it's probably going to read in all that information we just had to define. We're going to let the user, we have them start in that starting state. They enter in some input value, and then they transition, and we output what state they're currently in. So if I'm kind of thinking about it right now, what we're going to be doing, it's we start up our program, and we say we're in S0, and then we let them enter in a 0 or a 1, or they can enter in whatever they want, and then we go from that state to whatever that input determines the next state is. So in this case, if I start in S0 and I input a 1, then we should say, hey, we're in S1 now, input another input. We can keep doing that until the user enters exit, and then we're done. So let's look maybe a bit more of the exacts of what's going to be going on. So our task is to read in a text file that will contain a list of states separated by commas, okay? A list of inputs separated by commas, the starting state, and the list of connections. Okay, so that's a lot of stuff. So what's the first one? List of states separated by commas. So if we look at this example file we have, the states are S0, S1, and S2. Well, that makes sense, right? We have 3 states. It's based off that example we just looked at. So there were 3 states. There were 2 inputs, 0 and 1. And then we had a starting state of S0, which makes sense. And then the list of connections in the form of current state, input, next state. So from this we can see we start in S0. If we're in S0 and we get a 0, then we go to S0, right? If we start in S0, we get a 1, we go to S1. And if we go back up to the image up here, if we get a 0, we stay at S0. If we get a 1, we go to S1. And all that's the exact information in the same order as this table. So that's useful. So from there, we can make assumptions. We don't have to worry about whether they input something wrong or there's multiple states. So we can just assume that the file was written correctly, which is nice. And we can assume that the user enters stuff in correctly. And we just continue this process of asking until the user enters exit. And so we have a current session, an example of we have a current state S0, because based on our example, we start in S0. They input a number or, whatever that string is, comma separated. We can then go to the next state. they have them enter in another thing, we go to the next state, we enter in another thing, we go to the next state, you know. And so this is what we're probably going to be doing for C# and Python is we're going to have, you know, text files that we read in, we divide it out by commas and new lines, and we'll read in through it, and we'll handle it that way, and hopefully we can get an output that looks something like that. So optionally, we could also solve this problem in C. And when we solve it in C, we should also probably, since we're in C, we might as well take some liberties in adjusting how we're going to handle data, because C is a bit of a lower level, closer to a metal, some people might say it like that, where we have a lot more access to memory than something like Python does, and we can get a lot more precise in how we're doing things. So for our solution in C, we're going to use a bit more of an efficient methodology for how we handle data. And we're going to store things in bytes. So if you're not interested in C, you can skip over to the next part when we talk about, you know, what we're going to do from here. But for those of you who are interested in C, let's take a look at how we're going to more efficiently store our data. In this case, we're going to do everything as individual bytes, which we're just going to store in an unsigned char, and we're going to display them as hex values. So that means states and inputs, we're both going to handle them as unsigned chars. So their values can only be from 0 to 255, and we can go from there. So our input file is going to be a bit smaller. Since everything's in bytes, we're going to limit the number of states we can have from 0 to 255. We're obviously never going to have 0 states, so that would be boring. So we can just assume there's, you know, 1 to 255 states, and there's 1 to 255 inputs, right? Because we're not just going to have 0 inputs. That would also be boring. So, and then because we know how many states there are, instead of naming every state like we did in the previous one, we're just going to automatically assume what the indexes are going to be. We're going to essentially give them names ourselves, and we're just going to number them 0 to FF. You know, since we're thinking in chars, we're thinking in bytes really as hex values, that single byte can go from 0 to FF. And so if we have 3 states, they will be numbered 0, 0, 1, and 0, 2. Right? That's 3. 0, 0, 0, 1, 0, 2, all in hex. And if we have 10 inputs, remember that's hex, we'd have them numbered as inputs 0, 0 through 0F. So it's a little confusing. Why don't we jump through a little example from that exact same thing we looked at before. So we have 1 byte determining the number of states, 1 byte determining the number of inputs, 1 byte determining the starting state, and an S times I 2D array of bytes that tells us the next state given the current state and input. This is order in precedence by starting with state 0 and listing all next states given the 0 through I inputs, and the next state is listed with the next state given all inputs, etc. Okay, so that was a lot of information. So what does that really mean? So we have S times I 2D array. We have S states and we have I inputs. So that means we have 1 byte for every state input combination. And that makes sense, right? For every state and input, we have a next state we need to go to. And the array itself here, which is a 2D array, is the row is the starting state, the column is the input. So this byte here in this last set of bytes is the unsigned char value of the next state. So if we're in S0 and we get input 0, then we go to state 0. If we're in state 0, we get a 1, we go to state 1, right? If we're in state 1, we get a 0, we go to state 2. So when we start breaking that down, it will make a bit more sense. But then we can tell that there's 3 states, hence the 3 rows. We have 2 inputs, hence the 2 columns. We start in state 0, and then we have the transition table, which is a much more compact form than what we were doing previously. And so for reference, comparing the two, the previous way of storing all the data in a text file was 73 bytes, assuming that you did it on a Windows system, so you have 2 bytes for every new line character. Whereas our methodology here for C, we were able to store all the information in 9 bytes. And obviously we had tried some functionality for efficiency. And we'll look at that from there. So for those of you who kind of skipped over, we can now kind of jump back in for the kind of how are we going to do this? So it's a challenging problem. There's a lot of stuff going on, and so we need to think about how we're going to solve this problem. So first thing I always recommend is write it out. Try and make your own deterministic finite automata, draw it all out, play around with it for a little while. You know, don't make it easy. Don't spend just 10 seconds trying to draw it out and then think you know it all. Spend an actual good couple minutes writing one out. Try and see if you can write out the text file for it and then rebuild your DFA from the text file. And hopefully you should build out the same thing. And do it as, precise as you can. Step through every single thing. Don't take any shortcuts. Because if you can do it all by hand, you're going to be a lot better off being able to do it in the code. So we should take note, we don't necessarily need information about all transitions between states at all times. So this is kind of a note on how we're going to code it. We don't necessarily need all information at all times, right? If I'm in S2, I don't really need to know the transitions for S0. So when we write up the code for this, that's something we should keep in mind. We want all data accessible that we're actually going to need. So if I'm in S2, hopefully we have a way that I can easily access the transitions for S2. That's kind of a helpful thing. Additional features for those of you who need some additional things, we could handle the data file as a command line parameter. We could handle invalid inputs so we can inform the user that they entered in something wrong instead of just crashing, or the ability to save the current state as the new starting state. Those would all be nice things to add. But for the purposes of this project, we're just going to take some simplicities so that we don't have to try and handle all of this stuff at once. So, at the end of this, we also have to think that there are other things we could do with this beyond just the theoretical work. There are some more practical and maybe a little more fun things than just maneuvering around a state machine. And some of those things, that might be a command line game where you're having rooms connected together. If you think about that, that's kind of like a state diagram where you go from one state or room to another room. But you can also think about this as something like a traffic light or sensor monitors, or those embedded systems where they need an extremely efficient way of storing functionality. And if we kind of looked at that C program, we were looking at a very efficient way for storing a lot of functionality, going from one state to another, and then when you're in a particular state, you do something. That'll definitely help, and if you kind of look, there's a lot of other stuff you can look at from there. So, what are we going to do now? Now that we have our problem, what's the next thing for solving it? Well, I think the next thing we're going to do in hopefully the next video is break down the problem, try and see if we can do that step of breaking apart our own DFA, break it down to its text file and its byte file, and then rebuild it from both and see if we can do that. That'll be a good next step. And we're going to be able to come up with our own DFA. From there, hopefully we can take it, we can write it in C# one way, write it in Python another way, and both of those will be using the ASCII file that we'll create. And then lastly, we can jump over to C and use the byte file, the one that's just pure bytes instead of, text. And we can use that to create essentially the same DFA, but we're going to do it all in C and see if we can make it more efficient. So that's where we're going from here. I hope you guys are excited. It should be a great time to kind of look at problem solving. How do we break a problem down and really make sure we've mastered it for any kind of programming assignment that you get? That's kind of the goal of this series. So I look forward to seeing you in the next one.